Hello and welcome. My name is Marcel. I'm founding director of the Critical Media Lab at the University of Waterloo. And today, on behalf of my co-authors, I'm going to introduce a recently published paper, Sociotechnical Context Mapping for Responsible Innovation Pedagogy and Ethical Design. Over the past decade, calls for responsible innovation, or RI, in the tech industry have led to multiple declarations, policies, and corporate marketing strategies. Researchers of what we will call RI cite a definition provided by von Schomburg. RI is a transparent, interactive process by which societal actors and innovators become mutually responsive to each other with a view to the ethical acceptability, sustainability, and social desirability of the innovation process and its marketable products. The word transparent is instructive here, since it is perhaps the most crucial standard by which RI may be evaluated. For example, the Voluntary Code of Conduct recently released by the Government of Canada on the responsible development of generative AI lists transparency as one of its key principles as follows. Transparency. Sufficient information is published to allow consumers to make informed decisions and for experts to evaluate whether risks have been adequately addressed. In the same spirit, Stanford Center for Research on Foundation Models has broken down the transparency of Gen AI and AI systems into a simplified index. CRFM has looked at the most popular and powerful AI tools, scoring each individual model's practice of transparency against 100 factors. The chart shows growth in a positive direction for increased transparency. However, the most commonly used platforms, such as OpenAI's GPT-4, remain on the lower end of transparency scores across the board. A significant problem with this index is quite simply a lack of reporting on behalf of the corporations being indexed. To render an innovation process fully transparent for the sake of ethical analysis would require a very complex systematic assessment that considers the entire life cycle of a product, from the extraction of minerals required to produce it, to its impact on the workers involved in all stages of its production process, to individual end users and other indirect stakeholders affected by its use, to its end-of-life management. Moreover, the demand for transparency to support responsible innovation could potentially diminish the secrecy and hence value of intellectual property. And finally, claims about transparency can be mobilized as a corporate principle with very little substance, leading to false transparency, or a term coined in 2021 as transparency washing. In her book, The Atlas of AI, Kate Crawford suggests that the pursuit of full transparency in the examination of a technological product is an impossible goal that would require unraveling material architectures, contextual environments, and prevailing politics. These elements come together to form what we call a complex socio-technical system. And while a complete socio-technical system may not be traced accurately or completely due to its complexity and due to the inevitably partial nature of any observer's perspectives, an attempt to visualize such a system can be a critical exercise to teach the concepts of RI and to encourage ethical development of new technologies. Such an attempt is embodied in the anatomy of an AI system created by Crawford with her design collaborator, Vladan Joler. This complex graphic traces the many socio-technical networks involved in the creation, use, and disposal of an Amazon Echo. In Crawford and Joler's terms, socio-technical systems do not contain complexity, but enact complexity by connecting to and intertwining with assemblages of humans and non-humans. This fact makes the mapping of such a system all the more difficult. In a more ambitious project called Empires of Power, recorded here by the author at an exhibition in Paris, Crawford and Joler outdid their own attempt at modeling a complex sociotechnical system in The Anatomy of AI. Here, this contextual and political map of the history of technology fills an entire gallery space. Crawford traces this technique back to the methods of critical cartography. The technique is also aligned with the techniques of countermapping and gigamapping. These are all visualization methods designed to produce novel maps, often for political purposes, based on recontextualization of spaces and data. Gigamapping comes to us from systemic design, and it's referred to as super extensive mapping across multiple layers and scales, investigating relations between seemingly separated categories, and so implementing boundary critique to the conception and framing of systems. The study presented here by the authors introduces yet another iteration of these techniques. We call it Sociotechnical Context Mapping, or STCM. We define STCM as a pedagogical technique of mapping employed to visualize a broad ethical context for a given technology, focusing specifically on sociotechnical systems. STCM responds to contemporary needs cited by engineering education scholars. One, the need to enhance students' visual literacy, and two, the need to integrate tech ethics more fully into the engineering curriculum. The course study was conducted in the context of two types of courses, one, engineering communication, and two, information design. In both cases, students read and discussed a variety of journal and popular press articles related to socio-technical critique, white papers on responsible innovation and tech ethics, and depending on the course, they also worked with handbooks in either technical communication or information design. In course one, the context mapping exercise was applied to an existing tech product. First-year engineering students assumed the role of research interns at an interdisciplinary lab specializing in helping engineers understand the complex social, environmental, and ethical contexts of their projects and design. After selecting a specific technological object as a case study, students researched its socio-technical contexts, worked in groups to design a complex context map, and presented the design at a public showcase. In course two, students engaged in role-playing as responsible innovation auditors and offered their services to peers in a separate course that served as an introduction to engineering design. These peers became their clients. Students applied engineering communication skills while corresponding with their clients, researching the client's design project in the context of responsible innovation, and preparing a responsible innovation recommendation report that included a socio-technical context map. And finally, in course three, this is a sort of outlier since it involves engineering students, but not engineering students, sorry, but students from various disciplines, including English, fine art, computer science, and environment. This course asks students to apply principles of responsible innovation to a systems mapping project informed by best practices in information design. Similar to course one, students in this class selected a popular technological object as a case study. They researched its socio-technical context informed by readings in responsible innovation and worked in groups to design a complex context map. These students also presented the design at a public showcase alongside the first-year engineering students in courses 1 and 2. This study has shown that integrating SPCM into a course can align it with at least 3 graduate attributes of the Canadian Engineering Accreditation Board. The most obvious of these attributes is number 7, communication skills. This is why courses 1 and 2 are part of the engineering curriculum in the first place. But the course is not recognized for fulfilling attributes 9 and 10, though a strong argument could be made otherwise that the course does fulfill these attributes because it looks at impact of engineering on society and environment and focuses specifically on ethics and equity. That said, not all instructors of ENGL 192 make use of sociotechnical context mapping, and this technique is not a required element of the curriculum. So these graduate attributes cannot be attached to the course across the board. Our study has also shown that STCM can be effective for engaging students in real-world scenarios that apply interdisciplinary methods to model complexity. Students must deal with intricate and often unresolvable problems that require weighing the long-term and far-reaching consequences and benefits of an innovation. Students made discoveries such as the idea that apps to promote environmental stewardship draw on natural resources to function, and thereby might thwart their own purpose. Grappling with such complexity can challenge the expectation that students will acquire mastery over their subjects by adhering to principles such as efficiency and objectivity. STCM requires students to recognize that knowledge is situated, relational, limited, and often provisional. STCM also asks students to confront how systems of power, economic, political, and social, shape our technological milieu. And finally, the technique outlined in this study provides an easily replicable methodology for training students who are at once critical thinkers and critical designers. This is the ultimate goal of sociotechnical systems mapping. I'd like to thank my collaborators, Heather Love, Chris Rogers, Rebecca Sherlock, and Sarah Casey for the contributions to the study. I would also like to thank you for listening. Questions or feedback can be addressed directly to me at marcel@uwaterloo.ca.